Okay, good evening, everyone. Welcome to week 6. This week we'll focus on orchestrating AI agents, and we'll start working with LangGraph. As usual, we'll start today's class with a recap of what we did last week. So, who can help give us that recap of error handling and debugging? That was what we talked about last week. Larry, would you like to go? Your mic is unmuted.
Oh, I'm sorry, sir. But then, you don't want to go first today, sir, as always.
Okay, so who would volunteer to give us the recap of what we covered last week? No one. I actually need this recap, so I'm sure that at least some persons understood what we talked about last week and remember what we talked about last week before we layer any new content on that. And if your audio wasn't yet connected. That was what I was about to draw your attention to. Adobe, go ahead, please.
I think we actually did a lot last week. If you permit me, maybe I'll start with what we did on the last during the last class.
That's fine.
Um, so we did combining retries and fallbacks. We talked about the best practices for building resilient LLM based applications. We talk about hierarchy of resilience in cases where we attempt calling the primary components. For example, we gave example using one of the GPT models, using it on Grok, and then the the next stage of the hierarchy will be trying to like retry logic where there's transient error, and then we need to like retry the primary component with exponential backoff. And then if there's failure in few attempts, like say 3 attempts, we tend to switch to the fallback component. For example, we may run local models like Olama model, and then if there are still if the fallback component also fails, then we can raise an application error. We also went further to talk about observability and debugging, like unlocking the black box. We did uh, so many things about black box. Some of them are not quite clear to me, like the three steps, stages, like metrics, logs, and traces. We also did
Those are the three pillars of observability. They are the three major things that observability relies on. because metrics is the thing you capture, and tracing is capturing end-to-end details about a request or a transaction through the system, while logging is about
Timestamp.
capturing detailed details about an event or a transaction, as the case may be.
Okay, thank you. So we also did long chain callbacks, lens into LLM and agent behavior. There's a lot more that we did, which I'm yet to like go through. Something like key callback event hooks, the on-chain start and end, the Olama start and end.
On LLM, you mean? On
Sorry, sir.
LLM start, you mean on LLM start and
Yes,
on LLM end?
yes, those events are on LLM start and end, on to start and end, on LLM error and on to error. We also did logging and tracing using LangChain callback. We talked about basic callbacks. We talked about production logging, and then we did some kind of hands-on, some codes that we worked on that day. Before we did the last but not the least, advanced observability with Langsmith. So that's it briefly. I know there's a lot of explanation to all of that, but I just ran through them.
Okay, that's quite a comprehensive recap. So that's a good one. That's a good one. Thanks for that, Adobe. So I
Right,
think
thank you.
I have confidence to now get into the business for today. So today we will start by, well, after the recap for the business of today, we'll start by looking at what is the necessity for orchestrating AI agents. AI agents typically handle multi-step autonomous tasks, tasks that require multiple steps. If you remember, over the course of this training, we've talked about prompt chaining, where you break up the intent into multiple steps, right? And I mean, we've been looking at things involving different steps, tasks involving different steps. Now, if it's just a straightforward one-step task, it may not make much sense creating and deploying an agent to handle that task. If it's a straightforward one-step task, I mean, an agent may most likely be an overkill. So agents become valuable for handling multi-step autonomous tasks, multiple steps with minimal human intervention. Now, agents, they need to reason, to act, and to reflect. That this reason, act, reflect, they need to do this continually until, like, through going through a reason, act, reflect loop until the task has been completed, until the intent has been achieved. And managing these multiple steps and the different tools that the agent can use and the decision points in this reason, act, reflect cycle, it can be challenging. And that's why we need to orchestrate these agents. So orchestration is really about effectively coordinating this reason, act, reflect process or cycle, whichever one you prefer, but that cycle of reason, act, and reflect, coordinating it in AI agents, that is what orchestration is. And so focus this week will be mainly on orchestrating AI agents. And like I had mentioned at the beginning of this training, we'll be using primarily, we'll be working with LangGraph. Yeah, LangGraph is not the only library or platform, as the case may be. It's really a library but we'll get to that. It's not the only means, let me use that generic term, for orchestrating AI agents, but there are others, and we've looked at examples of some of these in our previous classes. But for this course, we'll mainly work with LangGraph. Now, here is a simple AI agent. It comprises an LLM with and tools that it can use. Sometimes tools, some people refer to them as skills. They are what gives the LLM the capability to act. So in that reason, act, reflect cycle that I talked about in the last slide, that action part is through the tools. So a simple agent is just an LLM with tools that you can invoke. Well, we already know that the LLM actually does not call the tool. It really makes a tool call request, right? But let's assume that that mechanism for invoking the tools whenever the LLM requests it is there. Let's just take it as a given. So a simple agent in that case would be the LLM and those tools that it can invoke when it decides that some action should be taken. And in this case, the LLM is the reasoning engine of the agent. It's the brain of the agent. It allows the agent to reason and select a given tool. You can reason and figure out which tool from the ones that are accessible to it is necessary for achieving the intent. And then, like I mentioned, those tools or functions is the same thing, or skills, if you prefer. They enable the LLM, the agent rather, to take action. And of course, there's, like I just said, and which we had mentioned in the previous class, when the LLM makes a tool call request, your code, you need to have code that will pass that tool call request, invoke the tools, and get the output of those tools and send it back to the LLM. And that code is your orchestration logic. It connects the LLM with the tools, enabling so that whenever the LLM requests that, hey, I need this tool called, it's that custom logic that will effect that tool call and retrieve the output from the tool call and pass it back to the LLM for the LLM to now reflect on the result from the tool and decide whether it's necessary to either call that same tool again or call some other tool or not to call any other tool at all, assuming it decides that the intent has been achieved. In this case, it will typically provide a response to the user depending on what exactly the prompt specifies. Any questions so far? Okay, so move ahead. At this point, we're going to look at some code. In the previous classes, we had tried to write a script that where the LLM is able to make tool call requests I remember there was a question in the Discord channel about I think somebody was observing that the LLM didn't actually answer the question in the query in that it didn't give the answer. It just stopped at a took or request, and I was explaining, yes, you need to implement code that will pass that to call request and then call the function and obtain the result, pass it back to the LLM. So we'll start today with implementing that custom logic without LangGraph. So I'm going to stop sharing my screen a bit, and then I'll pull up my IDE and I'll share my screen again. So just a moment, please. Please let me know if you can see my screen. Okay, Kenneth is asking, when are we supposed to use either LangChain or LangGraph? LangChain and LangGraph are not an either or thing. You can use both. It really depends on what exactly you're doing. I guess as we proceed, today and tomorrow, not today and Thursday, get a clear idea of what exactly LangGraph does, right? LangGraph is really for orchestrating agents, but we'll get to that. We'll get to that. So you can see my screen, right? Right. I believe you recall this code here. We had just a moment. I guess I have touched the code a bit. I've modified it a bit, but it's fine. Okay. Oh, I can solve this later. We don't even need this code, but this is just a static type, the type checker in the ID. Olanrewa, do you want to ask something?
Yes, sir. I'm sorry. I don't know. Maybe it's appropriate to ask at this time. Sir,
Yeah,
what
go
was it?
ahead.
What, sir?
Go ahead.
Okay, sir. What determines the time that we use prompt template or chat prompt template, sir?
The chat prompt template is a prompt template, but it's specific to chats, right? In a chat, you have a human message, as in the human prompt. A chat is like you're chatting with the LLM, but you can prompt an LLM without it being a chat. So the chat prompt template is optimized for chat workflows. Like ChatGPT is a chat-based agent. I don't know whether that clarifies it. So
Yes, sir.
you can use either one depending on your use case, really.
Okay, because as you told us now, system, human, I saw AI when I was doing some research. But I saw that in the example you gave us in class, you used chat prompt template, but there was no such in the example of summarize sentiment chain. But there was no, we didn't have the human AI. It wasn't a chat, but you used chat prompt template.
Yeah, that's what I'm
So
saying.
in the
A
chat,
chat prompt template is still a prompt template, just that it's optimized for chats.
Okay.
So thing is, what exactly are you doing? And then they may not have. It depends on your use case. You use the one that matches your specific use case. It's not that if it's not who determines it's a chat. It's still you. So I mean, it's up to you to decide what is your use case, which is more appropriate, and you use it. Both can work. Where
All
you
right.
can use a prompt template, a chat prompt template should also be able to fit into there, because a chat prompt template is still a prompt template, a list of substitution.
All right, sir.
Yep.
I'm grateful, sir.
Okay. So you remember this code where we wrote this script that we had three tools, I think: get location temperature, get local date time, and get offset from UTC. And to get local date time, you need offset from UTC. So typically, the model will need to call get offset from UTC first to get the offset, and then use that offset to call get local date time if the user's query is asking for the date time in a given location. So we did this, and um when we execute it, we get two call requests. So I think I'm having errors now. I think I must have modified this code when I was building the code for today's class, because it's based on this. Okay, got an unexpected keyword runnable. Well, that's fine. I won't waste time looking at this. I just was just showing this because what we are looking at today is based on it. Now, I went further to define the custom logic for um, executing the two calls when the LLM requests it, and that's what we want to look at now. So from the beginning, it's essentially the same as the one we did. I think this was last week or 2 weeks ago, thereabouts. The only thing I've done here is that I've modified the script to allow running with either a Grok model. If use Grok is set to true, it means it will run with a Grok model. But if it's set to false, it will run with an Olama model. And here I've tried to provide, well, we are going to use this model, but we can easily switch between any of these just for test purposes. And we may not be able to use all of them today in the class, but I will encourage you to also play around using different models and see how that the response changes with different models. I think we will also try different models today in class. Okay. Here, because I'm using a growth model, I need to get the API key, because the API key is needed to call the Grok API. So those are just the additional things I added to the code at the beginning. It's the same prompt and the same help functions, the same tools. The only thing here, I think, in this model, we had a method for the tools, not a method, a list for the tools somewhere. Yeah, available tools. Yeah. But to enable us call the functions, we need a mapping between the name of the tool and the function itself, the name of the tool and its function. So this is that mapping here is a dictionary of mapping a string to a function. We need this to be able to call that tool. And it's based on this that now define the available tools list. Yes, I could have still had the available tools list like this, but then it means that I'll have two different locations, two different sources of truth. This way, where the available tools list depends on this tool map becomes the source of truth for the tools that are available to the LLM. So I only need to make a change just to this if I want to add a new tool or remove any of those tools. Than having two different sources of truth. That's not very good software development practice, having multiple sources of truth. Okay. Apart from this tool map, it's still the same thing. Okay, here is where based on the value of use grok, I set the value for LLM. So you can either use a grok model if use grok is true, or uses an Olama model if use grok is false. And then we still bind the LLM to the tools. We still generate the chain just like in the previous code. Now, here is our custom orchestration logic. Of course, like I had mentioned earlier, this does not use LangGraph. It's a Python function that involves a loop. Typically, orchestral logics would most likely use while, but I've used for here, a for loop, because I specified a maximum number of iterations that it can run. But if you don't have a maximum number of iterations, you just run a while true loop until to keep on running until a termination condition um, is encountered. But here too, I have there's an what early termination. If a termination condition is encountered, it can terminate early before completing the maximum number of iterations specified. Now, exactly how does it work? First, as we get into the loop, firstly, we invoke the LLM, just like we did in the other code, and we get the LLM response. But we have um, a chat history list. The chat history list, it keeps the history of the interaction with the LLM. I think that should be then defined up here at the very beginning of the function. Now, it's a list that will typically contain different types of messages. If you look up here, we imported human message, tool message, and AI message. The human message will be for the user prompts. The tool message will be for the tool outputs. When the tool is invoked and it gives its result, it's that tool message that the LLM now sees to know when you pass the tool message into the history. The LLM reads that tool message and it knows this is the output from the tool based on the tool call request I made. And so it can, based on that, reason and decide whether it's necessary to make another tool call or not. And then the AI message is the response from the model itself. So the chat history is a list that contains any of these three. The elements will be any of these, right? So that's why the type hint is saying any. Yes, any is a bit wider than just those three, but it also works. We could also use the super class for those three. if we want to narrow it some more. Okay, so when we receive the output from the LLM, we append it to chat history to enable us keep that history, and so the LLM will be able to have access to the history and also be able to make decisions based on that history. Then the next thing to do is to decide, was there a tool call request in that output? Remember, the output is stored in the result variable. So we need to check whether there is a tool call request in the LLM's response. And if there's no tool call request, it means that we don't need to invoke any tool, since the LLM did not request for tool calls. And so if there's no tool call request, then it's the direct response from the LLM, and so we terminate the loop and return the response of the LLM. But if there's a tool call request in that in the output from the invoking the LLM, then we need to pass the tool calls from that LLM's response, that output from the LLM. And so we have these two messages lists where that we use for that. So for each tool call, in the tool calls field of the LLM's output, we extract the name of the tool, we extract the AGS, and we extract the tool call ID. For each tool call that the LLM requests, there's an ID. So we need this ID to be able to enable the LLM match each tool call request it makes with the response from that tool. And then we check if the tool name that we retrieve from the tool call, is it in our tool map? Recall the tool map we defined earlier, which maps the name of the tool to the function of that tool. So if the name of that tool is not in this tool map, it means that it's not a tool known to us and we cannot invoke it. Where's that? Here. So if the tool name is not in tool map, we don't know that tool, so we can't invoke it. We can only work with tools that we know, tools that are defined, tools that are bound to the LLM, tools that the LLM has access to. So if the tool name is in tool map, it means that that's one of the tools that we've made accessible to the LLM. Then the tool function will be that the function that corresponds to that tool name in the tool map that we have. And so we call that function with the arguments that the LLM provided in tool call request. So essentially just a normal calling of a function, except that this time we are passing out I will say the function itself, but it's actually the name of the function that we pass from the LLM's tool request. But then we retrieve the actual function using that tool name. We retrieve the actual function from the tool map, and then we call that function with the args that we retrieve from the LLM's tool call request. And then the result from that we get from invoking that tool. Remember that tools, that once we decorate a function with the tool decorator, it becomes a runnable. So we can use the invoke method on it, right? If you had not, it's possible to implement this without decorating those functions using the tool decorator of those functions, in which case we would not use invoke. We would just call it the normal way, toFunc. Then we pass the args to it. But in that case, we are going to use what's the term? Dictionary unpacking. So instead of just passing the two args, we are going to unpack it by adding two stars, two asterisks before it. So we would use dictionary unpacking in that case. But in this case, since we've used the tool decorator on those functions, the functions are runables, and so we can use the invoke method, which can take dictionary as input. Okay. Now we construct a tool message based on the output of that tool. So the tool message is the tool's output, which we cast as a string, and the tool call ID. Remember, I mentioned earlier that the tool call ID, which we extracted here, enables the LLM to match the tool's response, which we are trying to pass back to it as a tool message, with the tool call request that it made. So we construct this tool message and we append it to tool messages. So for each tool in that the LLM requested, in that response, in that output from the call to the LLM, we'll do this and we'll pass their responses, append it to the tool messages. And then eventually we are going to just a moment, please. Okay, sorry about that slight pause. Now we wrapped this in a try except block, so that assuming we encounter an exception, what are the possible exceptions? If the tool returns an error, maybe say we didn't pass the right arguments or something, we catch that, we should also inform the LLM about that. So we would also generate a tool message indicating that there was an error when we called that tool and providing details about that. And we also need to provide that to the LLM. So we also append that to tool messages. Now, this is if the name of the tool is in toolmap. If the name of the tool is not in toolmap, then we need to also let the LLM know that that tool, we don't know about that tool. And that's why we are appending a tool message indicating that the tool with that given particular name is not found. We don't know that tool, right? So when we are done passing the tool call requests and evoking the tools as appropriate, and appending the responses, the results from the tool calls into our tool messages. I think that's the name of the list. Then we append each of those two messages to chat history, and that's why we're using extend. So each of the two messages will be appended into chat history, and that's way the LLM is able to get access to the responses from the tool. Our custom logic has passed the tool call requests, called the functions, and provided the responses from the tools to the LLM through the chat history. The LLM has access to the chat history at each iteration. Remember, we have this loop that runs for at least max. I think it's a max steps. Now, if it exceeds max steps, then we return this message to indicate, hey, it has reached the maximum number of allowed steps, so it terminated. But the cycle will continue with the LLM requesting tool calls and our custom logic, invoking those tools and passing the result of the tool calls back to the LLM through the chat history. And whenever we get to the point where there's no tool call in the LLM's response, which is here. So it will keep on going through that cycle of reason, act, reflect until there's no longer any tool call in the LLM's outputs, at which point we'll return the AI message, which is where the LLM is expected to have provided the answer, the final answer to the user's query based on the information it retrieved from the tool calls. And so at this point, that's essentially just what's left is just to invoke this logic with, if you remember, our query is still the same query. What's the current weather? Okay. When we did this in class, we had 3 variants, and each of those variants had 2 branches. We had the variant of requesting only the weather, the variant of requesting only the time, and that of requesting both weather and time. And for each of these, we had called it with the LLM that had no tools bound to it, and with the LLM that had tools bound to it. Here, I've just extracted the variant that requests for both weather and time, and we are calling it passing that input to the LLM that has to bound with it, because that's exactly what you need for an agent. So we're going to try run this. I think it's currently set to run with the Grok model, Meta Llama 4, Maverick 17B, and instruction tuned variant. So we run this. Now, if I tried to include this step where at each iteration, it prints out the state. The state here is the chat history. At each iteration, it prints out the chat history. It was simply to be able to show you how the chat history is updated at each cycle of the iteration. Now, if you look here, the first step, that's step 1, the LLM, this is the LLM output. This is the current agent state. If you look at the chat history, now the first element in that list, chat history list, is the user prompt. What's the current weather and time in Kigali? And if you look, there is let's get to check whether there is a tools, there are 2 calls here. If you see, so you see there are 2 calls in the LLM response. Remember, the LLM response has been appended to the chat history. And so you see there are 2 calls in the LLM response. The first 2 is the get location temperature, which matches the request for weather. So the LLM made a correct decision there. And the argument he used was Kigali, which was the place we asked for its weather. Well, you can note the ID, but that's not really so important now. The next, it also requested for a call to get offset from UTC using the AG Kigali, which is actually what we asked it to do. That when the user asks for the time, local time in a given location, it should first call get offset from UTC to retrieve the offset value, and then subsequently call and get local time with that retrieves offset as the argument. And those are the only um, two calls it's requested. Get to get weather info and to get offset from UTC. These two, it's they don't depend on each other. So the LLM made these two calls in parallel, which is a good decision, which is a correct decision. Now, here is where it actually prints out. This is still part of what the logic is doing. Is it's printing out how many two calls were made. Helen requested two calls, which matches what we saw in the chat history. The first two call is get location temperature. It was executed, and the output from the tool is the temperature in Kigali is 21.2 Celsius. The second one returned from get offset from UTC, which matches what we saw in the two calls. It returned 2. If we check the no, that's not time. Yeah, the time dictionary, which is what the tool that gives the time is based on. We see for Kigali is 2 hours ahead of Greenwich, which is exactly what was returned by the tool. Now, in step 2, the LLM also makes a tool call. When you run this yourself, examine how the chat history updates after each step. Here you see that the LLM made one tool call, and the call was to get local date time. If we check the chat history here, we'll see that the argument he used there was the offset, that 2 hours offset that we retrieved earlier, and this is the output the tool gave, that the time is the same date, but it's 2 hours ahead of Greenwich of GMT. And then the third step does not have a true call, and so the loop terminates because that's the condition. And then the response from the LLM is printed out. The current temperature in Kigali is 21.2 degrees Celsius, which matches what we was retrieved from the tool. And the current time is 10:25, which matches what was retrieved from the tool. So essentially, with this custom logic that was implemented, we have built an agent that is able to provide weather information, well, really just temperature for certain African capitals, and then as well as the local time in these locations. Now, I'll run this with a different model. Let us see whether it gives us the same results or a different result. I'm going to use GPT OSS 120B, still on Grok. But before I do that, let me ask, does anybody have any question? Okay, so we continue. So we run this again using the new model that I've just selected. Now, notice that GPT OSS 120B is requesting one tool at a time. It does not make parallel tool calls, even though that it could safely call two tools in parallel that get location temperature and get the offset time or something. That's the name of the exact name, but the one that returns the offset from get offset from UTC. It could call those two in parallel, but it did not. It called only one tool at a time. First, it called get location temperature. It got a value from the tool. Next, it called get offset from UTC. It got a value, and then it called get local date time and got a value. But one thing I give to it is that even though it did not try to make use of that optimization of making parallel to course, at least it sequenced correctly. It did not try to call get local date time without first calling get offset from UTC. So in that, the reason is correct. It would have just been more optimal if it had made the parallel call, in which case it wouldn't have gone up to 4 steps. Now at step 4 is where it provided the final answer. And I think it's a bit more, this formatting is different from the one from the earlier Llama 4. I think it was Llama 4 that we used in the previous run. So it says Kigali, Rwanda. It has added additional information. Kigali, it has told you the country. Current temperature, provides the temperature. Local date and time, it provides the and then says, let me know if you need any more details. We'll just try it with another model. This time we use Llama 3.3, 70 billion parameters, versatile. Now, this particular model, I think it tends to just call the 3 tools, and it also tends to hallucinate the offset value when calling get local date time. It doesn't. It appears not to understand. I think this is the model. It appears not to understand that it needs to first call get offset from UTC before calling get local date time. So we run with this. Now, notice that in step 1, it made 3 tool calls. It called the 3 tools, and for get local date time, it actually used the correct value, but that's still hallucination. I will explain why I say it's hallucination. It used the correct value because it knows that Kigali, from its internal knowledge, from its training knowledge, its internal knowledge based on its training, it knows that Kigali is 2 hours ahead of Greenwich. So it got it correctly, right? Yeah, so you could say, yeah, it worked. But what if it's a location that it doesn't know the time difference from its training data? So essentially, it's hallucinating, which is even more concerning, given that the prompt says, if the user requests for the time in a given location, you should first of all retrieve the location's offset from UTC and subsequently use the retrieved offset in the retrieve. Okay, it's possible that because this prompt did not specify calling the tool, maybe it takes it that it's retrieving the information from its internal knowledge. So one way around this will be to specify in the prompt, make it clearer that, hey, you must call the tool for this. Do not use your internal knowledge. Because using internal knowledge can lead, in this case, it may lead to hallucination. I actually tried this with some fictitious location. It doesn't exist. So there's no way the location doesn't exist. So there's no way the model would know from its internal knowledge. And it just kept hallucinating most times with using UTC as a time zone, time offset of 0. So out of the 3 models we've used so far, this one, GPT 3.370B, I think versatile, it's performed the poorest. Yes, in this case, he gave the correct answer for time, but that's just because he used his internal knowledge. So, well, in this case, I guess it's also okay, but what if we can only conclude when we really give it a realistic, in a realistic scenario where it wouldn't have internal knowledge. About time zone is something that it should know, but so really that's fine, but it would have been preferable for it to use it. So I also know that I also tried to modify the prompts to insist that it use the tool, but it was still opinionated in using its internal knowledge for locations that it already knows the offset from UTC, and for fictitious locations where there's no way to know that it hallucinated with the value of 0. Okay, so for the final run from my end will be to use an Olama model. Um, yeah, I'll I'll try more than one Olama model. So to use Olama model, yeah, we'll use Grok to false. Let's start with Llama 3 1B. Am I right? Is that the name on Olama? Let me confirm this. Just a moment.
That's the name for Gemma.
Oh, Gemma. Okay. Yeah, Gemma 3 1B. Okay. Thank you. Okay, so let's use that. Gemma 3 1B, and we
Then we can actually
run.
be smart for this tax, sir.
Sorry, it won't work. I wanted you to see that because um just watch. Now see, it's telling you that Gemma 3 1B does not support tools. So you cannot use it for this. I think Gemma 2.2 or something also doesn't support tools. So you can't use you need to use a model that can call tools, a tool use model for building your agents. And that's just what I wanted to demonstrate. So we'll use Llama 3.23b. This one is be a bit slower than Grok models because it's running on less powerful hardware than the one in Grok's cloud. Okay, the first step has completed, and it's still called the three. You still try to call the three tools, but the call to get local date time failed because most likely because it didn't provide the correct argument. Let's check the two calls. You can see what's it actually. Yeah, two calls. Get local temperature. We used Kigali, provided units as Celsius, which is the default value. That's fine. Get offset from UTC. We call that correctly using location as Kigali. But get local date time. It provided location as Kigali, but that function does not have a location um, argument in its definition, so that's wrong. And then offset from UTC, instead of providing a value, it provided the name of the get offset from UTC tool. Now here, what I can infer from this is it's trying to obey the instruction in the system message, which says if the user requests for time in a given location, you should first of all retrieve the locations offset from UTC. So it knows that the get offset from UTC tool returns the offset for a given location. And so it provides the name of that tool in as the value for the offset from UTC argument. But I mean, that's not right. It wasn't smart enough to do the very right thing, which would have been to call get location temperature in parallel with get offset from UTC first, and thereafter call get local date time using the value it retrieved from the get offset from UTC call. So this is just to demonstrate that after you build, okay, let's go through to the end and see. Now, the smart thing really would be when it got a tool failure for get local date time, it should have tried again, right? Like error recovery to call it again now using this value. But we don't have, our logic does not cover this. Yes, we could try to add in our prompts that when you get an error and so, and maybe because you didn't have the correct values or something, you should try again and all that. Sure, we could do that. But my experience on this specific task with this particular model is you're still going to get, let's see what he gave here as the final answer. Yes, you're still going to get something similar. Here is mentioning, it seems like there was an error in executing the tool call for getting the local date time in Kigali. The error message indicates that the offset from UTC returned by get offset from UTC is not a valid number. Now, that is not true. The thing is that it tried to pass the get offset from UTC method or function as the arguments to the offset from UTC and the value of the offset from UTC argument in this function. But really, what it really passed was just a string, the function, the tool name. So it really didn't do the right thing, and it can't understand that. Okay, so it says, let me try again, and this time I'll use the offset to get the local date time correctly. First, let's get the offset from UTC for Kigali. Name, get offset from UTC. Now it understands that, hey, I didn't do it right. This is what I should do correctly, right? And it has provided this information. I will now do this. But the problem is that orchestration loop does not handle this because this final message does not contain a tool. And our orchestration loop logic is that if the LLM's response does not contain a tool call request, I'm trying to see where that is. Yeah, if not result, the tool call. So if there's no tool call request in the LLM's response in result, which is what we get when we invoke the LLM, then it takes it that the LLM has given the final answer and it terminates the loop. And that's what happened. So ideally, our logic should be able to understand, hey, okay, the LLM has figured out that it did the wrong thing in the previous in step one, and so it's figured out the right thing to do. So we shouldn't terminate. We should allow it to. We should look back again so that the LLM can now make this because this new plan that it has generated. The LLM is actually the reason, act, and reflect. In its reflection now, it's coming up with a plan to correct the error it made earlier, which is right. But then the failure here now is in our control, in our custom logic, in our orchestration logic. It terminated the loop because it didn't see a tool call, which was the logic it was using to determine whether it should invoke the tool or it should just return the response of the LLM. And so it just returned the response of the LLM. Any question? I forgot to mention that I had already shared this code. I already shared this code in the Discord channel. So I would like you to try this code yourself. Try it with different models. Try to see how you can solve this problem I just talked about, the problem of prematurely terminating the orchestration loop when the LLM is trying to correct itself due to an error it made, because it try to modify this custom logic so that you don't have such premature terminations, and also try to update the prompt template. This is just more like a basic prompt template. Try to update the prompt template to make it more robust, such that there's less likelihood of, I think, to minimize the likelihood of the LLM taking actions that suboptimal actions, like here, where it tried to call the three tools in parallel, even though two of those tools should normally be executed in sequence. Okay, so I guess no question. So I'll stop sharing and then we'll go back to the slides. Excuse me. Okay, so we'll continue with so we've just looked at trying to build an agent, a full agent end to end, without LangGraph. And we've seen, you'll appreciate that even more when you try it out yourself hands-on. We've seen that the difficulty of implementing orchestration logic that works well even in handles edge cases. It's difficult. It's a bit complex. Yeah, for simple, straightforward workflows, it's fine, but where it becomes more difficult to handle certain edge cases, and that is the agentic control flow challenge. So the complexity of the custom logic becomes more complex as you add more tools, reflection steps, and error handling. It becomes more complex. And so it becomes more difficult to implement because you need cycles where you rerun steps for refinement or tool use. You need branching where you make routing decisions, deciding which one of several specialized sub agents um, to call in the case of a multi agent system. And then there's also the need for persistence, that's reliably saving this state between steps. In the demo we had, we maintain state using the chat history list. So for complex use cases, it's really difficult to implement this control flow, this control logic or orchestration loop, right? And especially trying to have it make your agent reliable, particularly for handling edge cases like the one we encountered where the LLM made an initial mistake in trying to call the three tools in parallel. And even though it tried to correct itself, it realized the mistake, it tried to correct itself, our control loop terminated prematurely, not giving the LLM the opportunity to um, call the tools in the correct sequence in subsequent steps. So that's where LangGraph comes in. Okay, there's a message. Okay, is it this slide, Adobe? Adobe, is it this slide? You asked to see the last slide. Okay. Just let me know when you're fine so I can move ahead. Okay. All right. So LangGraph is a graph-based orchestration library from the LangChain ecosystem. It's used for building stateful multi-actor LLM-based application. Multi-actor in that you can have multiple agents in the same application, right? LangGraph allows you to model the control flow of the agents as directed graphs, and it replaces these opaque hard-coded custom logic like the one we had in the demo it replaces it with explicit and observable state machines. So the LangGraph models the agent as a state machine, and it simplifies the orchestration of the agent. So really, LangGraph helps makes it easier to solve challenges in orchestrating agents like the one we had when we tried to run the demo using Llama 3.23b, where our custom logic terminated prematurely when the model tried to correct itself. Now, LangGraph's core components include state. State is a record of the agent's internal, the history of the agent's execution. So it's a data structure that is accessible by all the components of the agent and can be updated by those components too. That way, it allows to maintain a persistent history of the agent's execution, enabling the LLM to reason with based on adequate context, and which helps improve the decisions it makes. apart from state, it also another component is nodes. The nodes refers to the components that actually take action in the agent. Action in this case is not just about tools. Yeah, tools are nodes, but the LLMs themselves are also nodes, right? And then edges are the connections between the paths between nodes, and they can be either direct or conditional. So a LangChain agent comprises nodes and edges connecting those nodes. And these nodes have access to the state. They can read the state, and they can also update the state. And running the agent, it simply involves moving the execution flow from one node to another through its edges, and continues that cycles, iteration, and branching based on the LLM's decision and the logic you implement until the LLM figures out that the intent has been carried out, and then the final output, the final response is provided by the agent. Any question?
So please, can you come again with the states? What does states actually mean, sir?
The states, it represents the I wanted to say internal, but the state that's coming. Essentially, the state is just a data structure, right? It's a data structure that contains a history of the agent's execution, at least for the current. Well, it depends on how you implement it. It could be current, but it maintains a history. It's a data structure that is accessible to the nodes in that agent, and that can be updated by those nodes too. And it keeps a record of um, like snapshots, if I may use that term, of the agent's execution history.
Is it like context, sir? Like context?
It provides context, yes, but context can go beyond state anyway. Just like the chat history list that we had in the demo, that chat history list is the state of the agent. Right. Does that adequately answer your question?
Yes, sir. I get it, sir. That is like the history of the agent's orchestrations, past
Agent
execution,
execution. Yeah.
executions.
Yeah.
And
Kenneth, state. You can think of state as memory, but when we say memory in AI agents, it goes beyond just state. So we are going to look at memory in some subsequent weeks. But you can think of it as just think of it as the history of the agent's execution. It's like takes snapshots, like
log, like
yeah,
logs.
okay, you could say logs. Just consider the chat history list we had in the demo, where it contains the user prompt, initial user prompt. When the LLM responds, that response is there. If it's a tool, outputs from a tool, well, if the LLM requested two calls, the outputs from those tools, execution of those tools is is added to the state. And so at each step, the state is updated based on the response from the LLM and the response from the tools, as the case may be, as when the LLM made two core requests.
Okay, sir. Please, how does it now relate to the nodes and the edges, sir? I'm just trying to find a link between the three.
The nodes have access to the state. The nodes can read from the state, and they can also write to the state. In this case, they update the state. If you remember, when the user made their request, what is the weather and time in Kigali, that was added to the state, right? It was added to the state, and the LLM had access to that. The LLM read that and uses that. The LLM, in its response, made two core requests. Those two core requests were added to the state, right? And then when your custom logic, your orchestration logic invokes those tools, when they execute those tools, the output from the tools were also added to the state. So at each step, the state is updated. And at each step, the nodes have access to the state. They can read the states to know what has happened. Of course, the state talks about the past, not future, what has happened. And then they can update the state with the most recent snapshots, if I may use that term.
So the
So
nodes LLM, sir?
nodes can be LLMs and can be tools and can be, in this case, your execution loop. Remember, we are talking about a graph. A graph has nodes, points, which are linked by edges, right? So the LLM is a node. The tools can be nodes. Any logic you implement, like the execution loop, can be a node. I guess this will become more apparent when on Thursday, when we actually try to implement these agents using LangGraph. So tools can be nodes, LLMs can be nodes, sub-agents can be nodes. Other components that you implement in your logic can also be nodes.
And edges, sir?
Edges are the connections between nodes. So any two nodes can have an edge between them. If there's an edge between this node A and node B, it means that the agent execution can move from node A to node B. But if there's no edge between them, then it cannot move from node A to node B. Remember that these edges they are directional, right? That there's an edge A to B edge does. If it's not a bidirectional edge, then you can only move from A to B.
Thank you, sir. I got the schema. I'll get the pedantic later.
Okay, does anyone else have any question? This is where we are going to end today's class. On Thursday, we'll now try to we'll now look at LangGraph in more detail, and then we'll try to implement that same agent using LangGraph. So we compare the implementation without LangGraph and the implementation with LangGraph. Okay, it appears there's no further questions, so I guess we'll call it a night, and then we meet again on Thursday. Thank you very much for. If you have any question, you can throw it. After this class, if you have it, okay. Alara, you want to say something? Kenneth, you want to say something? Go ahead, please.
Yes, sir. I want to just say, sir, please, do my very best to submit my stage 2, hopefully before daybreak. I will tag you as soon as I do so, sir. So I can have
Okay.
access to stage 3.
Okay,
Thank you.
that's fine. All right, that's fine. Kenneth, you wanted to say something?
Can you hear me?
Yes, loud and clear.
Finally. Okay, so Mike, I wanted to ask, is the edges the final part of the decision am I making, since it's also being connected to the nodes? And I can see like we have something called my direct and a condition. So like I wanted to know if the edges is part of the final part of like making a decision. Thank you.
Well, if it's about making a decision, then you're talking about a conditional edge. That's when you make a decision based on so and so condition. This is where we what we do. It's just like in what is that called? What's the name for the chart that is used to represent algorithms? The term escapes me. Anyway, if you have to take it, if it's a direct edge, let's say direct edge from node A to node B, the implication is that whenever you get to node A, the next node you move to is node B. That's a given, right? But if it's a conditional edge, so a conditional edge, it could be, let's say you have a conditional edge at node A. So it means that when you get to node A, based on the conditions, you will either move to node B or to node C. And that's the point of taking a decision. That's branching. So based on the LangChain graph, you can implement loops by going around till starting from one edge, moving and coming back to that same edge. That's a loop. You can branch using conditional edges. Flowchart was the term I was looking for. So think of it like a flowchart. Where you get a conditional, is this? If yes or if true, move this way. If no or if false, move this way. That's a conditional edge. But if it is from here, you must go to this next one, that's a direct edge.
Sorry, sir. So are those edges implemented by code like loops, if first statements, for loops, and the likes?
Well, in our the decisions branching is typically implemented through structures like if, else, switch, and so on, right? And looping is through while, for, and so on. But we may not even actually do all these when we implement with LangGraph. Yes, we may do some of that, but not so much in LangGraph. LangGraph simplifies the whole orchestration logic thing compared to custom logic that we try to use in the demonstration code we ran in today's class.
Okay, please, a final question, sir. When you told us about LangChain, you gave us some other options like AutoGPT, Creo, and
Sorry, did I say LangChain just now? What I said I meant
no,
was
sir.
LangGraph.
No,
Okay.
sir.
Okay, I
No,
wanted
sir.
to be sure. Okay, go ahead,
Yes.
please.
When you told us about those framework, you mentioned LangGraph, AutoGPT, Creo, and that's the fourth one. I can't remember. But then for
I think
LangGraph,
Llama Index.
yes, I remember. Thank you, sir. But for this, are there other alternatives apart from LangGraph?
LangGraph is for agent orchestration. Crew AI is for agent orchestration. You see, you can see, LangGraph is a library, an agent orchestration library in the LangChain ecosystem. So LangGraph typically works with LangChain. It's
Okay.
just that
Okay.
LangGraph is a library for orchestrating agents in the
Okay.
LangChain ecosystem.
That's fine.
For,
Thank you,
for,
sir.
for simple LLM applications, you don't need LangGraph. Like what we had been building prior to now, where you just have like a chain and so on. But where you now want to start building agents, or to start orchestrating agents, you can still do it without LangGraph, but LangGraph simplifies it.
Right. Thank you very much, sir.
Okay, you're welcome. All right, do we have any further questions? Okay, I guess there's no further questions, so I'll first stop the recording.